Good morning, class. So today's lecture is about the MOSFET. And before we start describing how the MOSFET works, let's just introduce it a little bit. And the way I'm going to introduce it is by talking about how it's used in a circuit. So first, going back to the bipolar junction transistor, okay, what you've learned is that the bipolar junction transistor is a current amplifier. You have a certain base current in, and you set a certain collector current out, and so the device amplifies the input current, which is usually at the base. And the MOSFET, which stands for metal oxide semiconductor field effect transistor, has this schematic here, where this is the gate, okay, and so that's at some voltage V sub G. This is the drain, and so that's at some voltage V sub D, and this is the source, and that's grounded. And you have a certain drain current I sub D that flows between the drain and the source. And that is essentially a function of the gate voltage that we're going to derive. And so it acts it's called a transimpedance amplifier. It produces a current in response to a voltage input. And the important thing about this is that the gate current is 0. And so, just checking my focus here. That looks pretty good. The great thing about the MOSFET, or the metal oxide semiconductor field effect transistor, is that there's no input current. And so if you are making stages of the devices, you don't have to worry about coming up with that current. It doesn't draw any power. And so it can form the basis of very complex circuits, which is basically all of our digital circuitry or computer circuitry. So it's an extremely important device, and I guess you would have to say perhaps more important than the bipolar transistor, mainly because of that characteristic. Okay, so with that small introduction, let's start talking about how the device works. So let's start drawing it. So we're going to take a p-type substrate, and then we're going to implant or otherwise diffuse in N regions. And we're going to put an oxide here. And on top of that, we're going to place a metal gate. And I'm going to extend my drawing three-dimensionally. And this is VG, and I'm going to start telling you what they are. It's going to be a positive voltage. And this is VD, the drain voltage. And as we discussed, the source S is usually grounded. And additionally, the substrate is usually grounded. Okay, so there's our device. Before we go on, this is what's called an N-channel MOSFET. And it's because, as you'll see, the device forms an N-channel, and that's how it works. There are also P-channel devices where you flip N and P here. But for the same reason, when we covered bipolar transistors, we did the NPN, because for the NPN, all the voltages and currents are positive. It's the same thing here. For the MOSFET, we're going to cover the N-channel. Because all the voltages are positive, the gate voltage is positive, and the drain voltage is positive. Now, first of all, think in terms of if the gate voltage is 0. Now, technically, what I mean by that, because we're going to talk about a threshold voltage, I'm saying that the gate voltage is less than the threshold voltage. In fact, the threshold voltage could be negative. But let's just go on from there. If the gate voltage is less than the threshold voltage, then this just looks like this, and there's no conduction from the drain to the source because there's nothing to conduct there. Remember, if you have a positive voltage on the end, this is reverse biased, and so there's no conduction across here. Okay, now, as soon as we apply a gate voltage sufficiently high, what it's going to do is going to form a narrow layer or a thin layer of electrons underneath it. And then that can act as being a conducting channel. And so, of course, that's called the channel. So we're going to draw a coordinate system here, X. Where this is L, the length of the channel. This, by the way, is W up here. This is X equals 0. And I'm just going to start analyzing it, and then we might go back and forth a little bit to make things more clear. So what I'm going to plot first is the voltage V, which is the voltage in the channel. Now, so I'm assuming that the channel's formed, which we'll talk about, that in a little bit. All right, so what is the voltage in the channel? Well, okay, on this side, 0, because the source is grounded. And on this side, it's V sub D, because it's connected to the drain there. And in between, it does something. Okay, we don't know what it does, but there's some variation of voltage. And we don't care. We don't care what that is. You'll see that that drops out of the analysis. Now, the next thing we have to do is we have to figure out what the charge is in that region. Now, to do that, we have to go back to your early electrical engineering classes and talk about capacitance. Okay, now if you remember, capacitance is a defined term. It's defined as charge over voltage, all right? And it's, basically for any two-conductor system, the capacity to hold charge at a certain voltage. So it's a definition. Now, I'm going to make one slight modification here. I'm going to put prime up there. So now this is the capacitance per unit area. And Q then is the charge per unit area in the channel. Now, so I can write that if this is Q sub n prime, the charge per unit area in that channel, okay, I can write that as, okay, some capacitance. Now what capacitance? Well, the capacitance of the oxide, because that's the thing between the gate and the channel. Times, all right, now the next step, okay, you have to work with me a little bit here, because, okay, what voltage, there's a voltage that goes here, right? Q is C times V. Okay, the, the voltage there is the voltage between the gate and the channel. But, okay, remember, there is no channel until the gate voltage exceeds a certain threshold. And so, here is VG minus V threshold. All right, now, so it's in the formula, the voltage there is not the actual voltage across the oxide, but it's the voltage above the threshold voltage. And I mean, you can think about this two ways. One is that, okay, if VG does not exceed the threshold voltage, there is no channel, so nothing has happened yet, so none of this makes sense. The other way to think about it is that if you sort of walk through it in a lot of steps, okay, really this formula is for a change in charge over a change in voltage. And the change in charge is Qn, the channel charge. Okay, and the change in voltage is the voltage above the threshold. So, you know, I sort of, you know, danced through that a little bit fast and loose, but just, you know, and perhaps read through the notes and where it's explained in more detail. The charge in the channel is the oxide capacitance times the gate voltage above the threshold voltage. All right, and I left out a term, sorry. Okay, so it's the gate voltage minus the threshold voltage, but also minus the voltage in the channel itself. All right, and the way to think about that is that, okay, over here, the charge per unit area is just the gate voltage minus the threshold voltage. But as I move along here, my voltage goes up, and so I have to subtract that off to get the charge as a function of position, which I'll draw right now. Okay. By the way, just completing this here. Okay, remember C oxide. Remember your formula: permittivity times area divided by thickness. So that's epsilon oxide times times the area of the gate divided by the thickness of the oxide. So C ox prime is just epsilon oxide over T oxide, the capacitance per unit area. All right, so the next thing is I'm going to draw what Q is as a function of X. All right, Qn prime. All right, so we just look at the formula here and we sort of get it. It starts out at a higher value, okay, whatever that is, because that's where V is 0. And as V increases, it goes down in some way. And again, we don't really care what. All we need to know is that that is given by C oxide prime times Vg minus V threshold minus V, where V depends on X. Okay, now what I'm going to do is we're going to write down what the current is in the channel. All right. Okay, so let's just do it, and then we'll back up a step, and you'll see it all makes sense. So, what is current? Okay, and I'll label it as ID. All right. That's equal to J sub D, the current per unit area, times the area, okay, of the channel. Now, here you have to be careful and think about it correctly. When we calculated the capacitance per unit area, that was this area here, okay? But now we're calculating the current flowing through essentially what is a resistor. And so the area, this is the channel cross section. All right, that is, I'm running out of, it's this thickness times that. All right, now we're going to make up something T channel, the thickness of the channel. Now, for those of you that have covered this before, you know that there is no thickness of the channel. It's infinitesimally thin. Okay, but you'll see it's going to drop out of things here, and so we won't need to worry about it too much. All right, so let's just keep going here. Now, what is JD? Well, okay, flux theory, remember, that's the charge per unit volume, rho, times the drift velocity. But what is rho? Rho is Qn prime, the charge per unit area, divided by T channel. And what is V drift? Well, that's the mobility times the electric field. So I can write this as Qn prime over T channel mu E. Now here, what is E equal to? Remember, it's the change in voltage over distance. This is E. That's slope. Okay, so let's put it in. dE dx. All right, that's JD, the drain current per unit area. Remember, and then A okay, that's the cross section. So that's this times the thickness of the channel. It's sort of, that cross-sectional area that I'm trying to indicate there. So it's W times T channel. All right. Oops, speed. And you see nicely that the T channel cancels out. So, we sort of made it up to do the analysis, and then it went away, so we didn't need to worry about the fact that we had made it up. Okay, now before we go on with the derivation, let's just go over something so you know that I'm not trying to trick you. ID. Now, you may have like kind of thought that, well, wait a minute, okay, ID, yeah, that's JD, the current unit area, times the area. But it's like, okay, ID where? Where are you talking about here? Well, everywhere, okay? And the thing is that, of course, from Kirchhoff's law, ID is the same all along here. The current can't go away anywhere. It has to be the same current. It doesn't depend on distance, all right? And you can see that, okay, from this formula, because the charge in the channel is going down as I move across it, all right? But the slope of the voltage, okay, is going to be going up as I go across it. Now, how do I know that? Well, because I know Kirchhoff's law, and so I know that ID is going to be a constant across the channel. And if you went through and you figured out what V exactly was and calculated dV dx and saw that it was increasing, and then calculated Q and saw that it was decreasing, you would find that the product of these two things is a constant because it has to be. Okay, Kirchhoff's law. Kirchhoff's current law can't go away. All right, so having noted that, let's continue this here by plugging in our numbers here. So I'm going to collect some terms. So basically, I got mu, the mobility, I have W, the width, T channel went away, Q is up here, C aux prime times VG minus VT minus V, and then dV dx. So that is ID. ID, the drain current. Now, the drain current where? The drain current everywhere. Okay, the drain current is equal to the mobility of the channel times the width of the channel times the oxide capacitance per unit area, which is given by this, times the gate voltage minus the threshold voltage minus the voltage in the channel, which is a function of x, times dV dx, which of course is also a function of x. And it has to be that this product, even though this is V of x, and this depends on x, that this is independent of x. All right, it has to be. Okay, so let's just move along. Now, you may be thinking, okay, well, we don't know V, so how are we going to figure this out? Okay, and now's the time I have to go to the next board here, and I have to keep track of my focus to make sure it doesn't focus on me instead of the board. So let's just continue moving here. All right. Now, you look at this and you see this equation, and I'll just do it, but you know, this is basically freshman calculus at this point now, because whenever this is a differential equation basically. It's a first order differential equation which you can just solve by putting the dx on the other side. So let me redistribute terms. So ID on one side, and I'm going to put the mu w the aux prime over there. And I'm going to put the dx over there. And then I'm going to leave this over here. So all I did was I rearranged the terms algebraically. Now, whenever you have a dx on one side and a dv on the other side, all you have to do is then just integrate each side. Okay, what are the limits of integration? Well, here you're integrating with respect to x. So you're going, I'm just keeping track of my focus, you're going from 0 to L. Here you're integrating with respect to voltage, and so as x is going from 0 to L, V is going from 0 to VD. All right, and okay, okay, so let's just do the integral. The integral is pretty easy, right? Because this is a constant, so that becomes Vg minus Vt minus V, and this one is V squared over 2, and that's between 0 and Vd. And this one is just the integral of dx, which is L. So I have ID over mu W C oxide prime is equal to that, just plugging in, Vg minus Vt times Vd minus Vd squared over 2. So you see, when you go through the analysis, you don't need to know how either V or Qn depend on X, because you basically integrate it out. See, you know VD, you know V3. Well, we'll talk about the V threshold in a little bit. Okay, so just that's our answer. I forgot L. See, because when you integrate it from 0 to L dx, that's L. Now, let's look at this and think about this a little bit. What I'm going to do is, let me do it over here. So I'm going to plot the drain current ID versus VD for a particular VG. And when you plot this, okay, it's going to look like that. Now, what's going to happen, what you'll see, so this is for some VG, is that, okay, just let's just walk through it maybe very quickly. If you take the ID dx, right, that's proportional to Vg minus Vt minus Vd, right, just taking the derivative, right, because that is just Vd, and so that becomes that, and that becomes, when I take the derivative, 2 cancels minus VD. Okay, so what you see is that when VD gets to VG minus VT, the slope is 0. Now, concurrently, if you think about it, if you go back over here, what's happening is that when VD reaches VG minus V threshold, then at the drain, the Q goes to 0. All right. Let me just say it again in words. At this point, where VD equals VG minus VT, just looking at the formula, if VD, which is V at L, equals VG minus VT, Q goes to 0. All right, that's called pinch off. Now, what happens next is a little bit difficult to explain, but it's sort of naturally what you would think. It just continues on at that level. So ID is equal to, and we have to write for 2 regimes, okay? It's equal to mu W C oxide prime over L times this VG minus VT times VD minus VD squared over 2. Okay, it's equal to that for VD is less than VG minus VT. And for VD greater than VG minus VT, it's just equal to whatever whatever it was. Okay, you just plug in that, and if you plug in VG minus VT, that becomes VG minus VT squared. That's VG minus VT squared over 2. So there's a 2 that comes out there, times VG minus VT squared. So I just want to check my, yeah, I'm in focus. Stay in focus. So we've derived the current voltage characteristics, okay, which basically, okay, you know, for different values of VG, it's going to, you know, do that, and basically, all right, that is for VG equal V threshold, right? Because if VG is the threshold voltage, okay, then it's going to be 0 all the way across. So basically what we've shown is that when VG exceeds the threshold voltage, we start to get current and we get this characteristic here. Up to VG minus V threshold, it goes as this, and it has sort of this, you know, curvy shape to it. And then once it gets to that point, well, actually, okay, I drew this wrong because VG minus V threshold is changing. See, for this one, VG is smaller, so it gets to that point, VG minus V threshold at a lower VD. And we sort of have this sort of progression of curves where it's curvy up to a point that's increasing, and then it's flat, given by this value. And that's it. So, you know, you can see that even though the MOSFET is such an important device, and in fact we could spend lectures on it, mini lectures, we can derive the current voltage characteristics in one lecture. And so, you know, and we've walked through it. I want you to walk through it again at home. And the reason why we could do it is because we assumed that there was a certain threshold voltage. Now, I'm not going to go over, you know, how you calculate the threshold voltage. There's some discussion in the notes about, you know, how to do that or what goes into that. And in fact, much of the complexity of understanding from a semiconductor device standpoint, the MOSFET, is in trying to understand what determines the threshold. Okay. Here, and again, this is why I call this a working knowledge of how MOSFET works. We just assume that it's some value, some voltage that someone told us. Now the thing is that the reality is that you can walk through what determines V threshold, and I do in the notes, and I want you to read that. Given that this is the last lecture of the semester, I'm not going to try and walk through that too much. And part of the reason why is because even though you can go through the physics which determines V threshold, and things called flat band voltage and stuff like that, it usually turns out that the second order effects, which are things like charge in the oxide and such, they can start to have a dominating effect on what V threshold is. So in fact, you tend to measure it when you produce the device. And so much goes into V threshold, and it's so difficult to calculate from first physical principles for real that usually it is just treated as a parameter. Now, treating it as a parameter, okay, V threshold, you know, we've discussed it in terms of it being positive, that basically the gate voltage has to exceed a certain positive value in order to start getting a channel and current. However, even though it kind of sounds, you know, like it doesn't make sense, you can design a device where V threshold is as negative. All right. Now, if you know, this drawing is for the gate voltage increasing above a certain positive value. Now, the thing is that if this is for sort of V threshold greater than 0. If V threshold is less than 0, which it can be, all right, you can have where, okay, this is for the gate voltage equal to 0. All right, and so you can have devices where as I apply a gate voltage, the drain current actually goes down. And so these are enhancement and depletion devices. And so what you see is that V threshold, not only is it something that's very difficult to determine from first principles, it's something that you can sort of engineer around first principles and get it to do whatever you want. And so you can make that part of the design of the device, is designing for a particular V threshold, which can be positive or negative. Okay, so that was all I was going to cover on MOSFETs. We'll go over it in the chat lecture, and after that, next week, I will produce some homework on MOSFETs, which will be the last assignment of the semester. Okay, thank you.